Namaskar. I am Dr. Aarti Chaudhary, Assistant Professor in the Department of Ancient Indian History, Culture and Archaeology at Vasant Kanya Mahavidyalaya, Banaras Hindu University. I welcome you once again in this 12-week course titled History of Science and Technology in Ancient India from Harappan Civilization to 7th Century CE. Slowly, we are uncovering the science and technological aspects of ancient India in this series. Now we are here in the stage of Module 2, Lecture 3. The title of Module 2 is Science and Technology in Harappa Civilization, and the lecture title is Harappan Mathematics. In our last lecture, we have discussed about the Harappan metallurgy, the different metallurgical techniques, the different metallurgical aspects of Harappan civilization, and now we are going to discuss about the Harappan mathematics. The learning objectives of this lecture is to know the calculation pattern followed by the Harappans, discussion on the archaeological sources, and to understand their weight and measurement numerals. In this topic, we are going to discuss the different parameters such as introduction, key site with mathematical evidence, unit of measurement and instruments, Harappan weight system, Harappan scale and ruler, bricks proportion, standardization and engineering precision of the Harappan civilization, urban planning and mathematical precision, advanced hydraulic engineering of Harappans, mathematics in maritime trade, Lothal's dockyard and hydro engineering practices, as well as comparative analysis with other civilization. The Harappa civilization is amongst the most advanced early civilization in terms of mathematical and metrological developments. The consistency observed in their weights, measurement unit, urban layouts, and architectural design indicates a profound comprehension of mathematical principles. Archaeological excavations at prominent Harappan sites such as Harappa, Mohenjo-daro, Lothal, Dholavira, and Kalibangan have uncovered evidence of advanced numerical and geometrical knowledge. The presence of meticulously calibrated weights, standardized bricks dimensions, and well-designed drainage system suggests that the Harappans developed a sophisticated measurement system potentially based on a decimal or binary scale. We know that we don't have any literary sources which focus on direct mathematical calculation which gives information regarding the mathematical aspects of Harappan civilization, because their script is not deciphered yet, but the on the basis of archaeological evidences we can say Harappans were expert in calculation. The key site with mathematical evidences, which are Mohenjo-daro, Harappa, Lothal, Dholavira, Kalibangan, and many more. Standardized bricks, weight, grid-based planning have been reported from Mohenjo-daro. Linear measurements, drainage slope calculation is we can show in Harappa. Ivory scale dockyard proportions we can see in Lothal. Geometric city planning, water reservoir designing, we can show in Dholavira, as well as brick ratio in Kalibangan. Unit of measurement and instruments. If we are seeing that the Indus inch, then smallest recorded unit of length measuring approximately 1.704 mm, identified from the ivory scale found at Lothal and centrally regulated metrological framework. Measuring instruments, that is cubit rods, ivory scale, calibrated rulers, which is found from the different site and gives information regarding the calculation pattern and mathematical observation, mathematical knowledge of the Harappan civilization. From Mohenjo-daro and Harappa, numerous inscription and stone weights have been reported. The Indus script is not deciphered yet, but a large number of weights have been studied by the scholars. On the basis of scholars, these weights were intended to be fractions or multiple of the uncia. 288 specimens of small cubes of chert have been shown to fall under 7 distinct groups. By assuming 1 uncia equal to 27.2 gram, these groups are as mentioned on the slide. These are the calculation pattern which reported from the archaeological evidences by the different scholars. Uncia is a unit which decoded by the scholars like 1 by 16 uncia is equal to 1.7 gram, 1.8 uncia is equal to 3.4 gram, 1.4 uncia is equal to 6.8 gram, 1.2 uncia is equal to 13.6 gram, 1 uncia is 27.2 gram, 2 uncia is equal to 54.4 gram and 5 uncia is 136 gram. The discovery in large number from both the side of the weight specimen of mass 13.6 gram. Few metal scales were also found, probably for weighting light and precious substance. These are basically related to the mathematical calculation on the basis of findings, on the basis of material remains. Hence, see the slide where Indus scale, which is reported from Mohenjo-daro, it is a very important scale, and fragment scale have been reported from Mohenjo-daro. It was made of a shell measuring 6.62 centimeter in length by 0.62 centimeter. The scale shows 9 parallel lines cut with a fine saw. One of these lines is marked by a fine circle and the sixth line from it by a dot. The measurement of these 5 intervals show 1.32 inch, making the distance between two lines equal to 0.264 inch. Berryman called it Indus inch, its calculation exactly equal to 2 Sumerian shushi. Another significance of the Indus scale is that 25 Indus inches equal 33 inches, which again equal the yard prevalent throughout North India in Akbar's time. According to Mackay, probably this scale was 13.2 inches long and hinted at a decimal mode of dividing and measuring lengths such as was characteristics of ancient Egypt and Elam. So we can see, though the scale is not present in its complete body, but the fragment indicate that this is made by a very perfect calculation mind. One another example is of scale and inscription found in Mohenjo-daro show that numbers were represented by vertical stroke as we can see on the slide, arranged side by side or in lateral groups. This might probably be some kind of rod numerals, of which we have many examples in other ancient cultural area, notably in China and the Mayan, it is like this. These are the symbols of the measurement. We don't have an idea that how they represent higher numbers like 100, 200 in this pattern. We can assume that they want to say on behalf of these lines that small number like 1, 2, 3, 4, 5, etc. But what was their expression in terms to present 100, 200 or big numbers? We don't have any idea regarding this. But the vertical and horizontal lines like this later survived in Kharosthi and Brahmi numerals as well. Harappan weight system. These are also very important in terms to understand the calculation pattern of Harappan civilization. They were made from chert, statite, agate, and quartzite and were generally cubical in shape, but some of them were in sphere, cylindrical, and conical forms. Geometric progression 1, 2, 8 oblique 3, 4, 8, 16, 32, 64, 160, 200, 320, 640. These are the progression, multiple progression mentioned by the Harappans in their calculation pattern. The calculated unit weight is 0.854 gram, while the maximum recorded weight is 10970 gram. Weight from Harappa indicates that they were used at city gateways, likely for taxation, while their presence in large residential structures suggests a role in commerce. Lothal weights are based on the decimal system, different from the standard geometric sequence. The most common weight is approximately 13.7 gram, which is in the 16th ratio. This ratio is later proceeded in many historical period as well. Harappan weights in Mesopotamian trade centers such as Magan and Dilmun. So, in terms to understand that the Lothal, Magan, Dilmun, Harappa, Mohenjo-daro, there is finding of different weight. Possibly, they were practiced it on the basis of their requirement and demand. Harappan weight system, ratio and units. Here is some example like weight category, ratio and material. 1 unit is equal to 0.8525 gram and the material is made on chert and statite. Second unit 1.705 gram and material used chert and statite. 4 unit 3.41 gram and the same material used for the weight. 8 units 6.82 gram and chert and statite used for the weight. 16 unit 13.64 gram that is also made by chert and statite. Possibly chert and statite easily available and they are good for the weight measurement tools. Harappan scale and ruler. Lothal ivory scale 27 graduation over 46 mm gives a unit of 1.88 mm. The 6th and the 21st graduation appears longer, perhaps pointing to a decimal intention. Mohenjo-daro ruler 9 inside dividing lines creating 8 divisions of 0.706 mm each. A dot and a circle were incised 5 graduations apart showing an equal interval of 1.32 inches make the distance between two consecutive lines equal to 0.264 inch. Harappan bronze rod It is divided into four divisions of 9.34 mm each, being 1.39 times larger than the division of Mohenjo-daro scale. It is again made on the basis of on the requirement of their demand. These tools ensured accuracy in trade, architecture, and engineering, reflected in bricks proportion, which is 1 is to 2 is to 4, city layouts 5.4 ratio, and statized street width. So we can see they choose the material which was accurate for the calculation. In scale, they choose ivory scale, which is just the ivory has no any relation with the temperature changing, so it is just they selected for the accuracy maintaining maintenance in a particular time range. So not only they select material, on the basis of demand they use it, and on the basis of reason they change it in the parameter of calculation and measurement. If we see the bricks proportion, then it is also an important example for the understanding of calculation and mathematical perspective of Harappans. It is uniform ratio like 4 is to 2 is to 1 and 1 is to 2 is to 4 ensured structural stability across sites like Harappan, Mohenjo-daro, Kalibanga and Dholavira. 1 is to 2 is to 3 ratio of bricks can be seen in the early phase, and later they developed it as 1 is to 2 is to 4. I already said they continuously developed their own town plan, and on the basis of requirement they changed their calculation on the bricks and the other things. Standardized standard size is 28 into 14 into 7 centimeter. Seismic resistance proportion likely enhance earthquake resilience. Multi-story buildings consistent size enable efficient stacking. Urban planning uniform bricks supported advanced drainage, street and reservoirs. Architectural legacy ratio continued in later Indian construction, which is reported by Michel Danino as well. So these are the basic reference which gives information regarding the mathematical and calculation knowledge of Harappans. Urban planning and mathematical precision. Grid based street planning. Streets intersected at right angles, forming an orthogonal layout with main roads up to 9-meter wide and secondary streets averaging 3 meters. Astronomical precision. The alignment of streets with cardinal directions suggests knowledge of celestial observation and timekeeping. Harappans were well known to the astronomical aspect as well, and they why I'm saying this because their agricultural knowledge, and they used to go other world, other country for their trade, and it is not possible without knowledge of direction, without knowledge of astronomy, without knowledge of a star. So we also found compass from Lothal, which indicate that the Harappans were well known to the astronomical aspect. Standardized house layout. Residential structures followed a modular design, often with courtyard and uniform room size, reflecting metrological consistency. If we see in the drainage system, standardized bricks ensure uniformity in drainage construction. Width and slopes were carefully calculated for a steady flow of water. Reservoir and grade path indicates knowledge of volume calculation as well. Fortification and public architecture. Sites such as Dholavira featured massive gateways, bastions, and conservation structures, highlighting civil engineering expertise in this form. Mathematical ratio in construction, the use of 1 is to 2 is to 4 4 is to 2 is to 1 and 5 is to 4 proportion in brickwork and city layouts indicate a keen application of geometric principles. Mathematical precision in Harappan public building. It is divided into 4 groups like structure and the site from where it reported, dimensions and mathematical feature. Great Bath, which is very important structure of Harappan civilization, situated in Mohenjo-daro. Dimension is 12 meter into 7 meter into 2.4 meter. Symmetrical bricks lining for water retention. We can see on the basis of the structure, they build their dimension and their different features. Granary reported from Harappa 50 meter into 30 meter. Proper ventilation based on proportional air circulation. If we see the dockyard reported from Lothal 218 meter into 37 meter into 4 meter. Tidal calculations for water flow regulation. Reservoir found from Dholavira 73.4 meter and 29.3 meter into 10 meter. Volume optimization for long-term water storage, as well as fortification from Kalibanga, mud bricks, walls, geometric layout, even spacing for structural stability. On the basis of this table, we can say different structure represent different mathematical concept of Harappan civilization. Advanced hydraulic engineering, which is also show the mathematical observation and the presentation of calculation scientifically by the Harappan workers, Harappan artisan and the Harappan people. Reservoir and water storage. Dholavira had multiple rock cut reservoir, the largest measuring 73.4 m into 29.3 m into 10 m, strategically placed to collect and store monsoon water. Lothal Dockyard featured a sluice gate water management system demonstrating expertise in hydrodynamics. Step wells and embankments. Excavation at Mohenjo-daro and Harappa revealed bricks-lined step wells and embankment designed to control water flow. Several deep wells with staircase have been found in Dholavira along with large reservoirs and embankment. Mathematical precision in water management. Engineers utilized volumetric calculation to optimize water retention and distribution. The layout of channels, drain, and soak pit followed plant gradients, ensuring efficient water flow and waste disposal. As well as in the group of drainage and sanitation, we also found mathematical and calculative evidences, just like covered drains lined with bricks were constructed beneath streets connected to household drainage system. The presence of silt traps and sedimentation tanks indicate early water filtration techniques. Mathematics in maritime trade, Lothal dockyard and hydroengineering. The dockyard at Lothal is one of the earliest known dockyards in the world, demonstrating a highly advanced understanding of measurement, geometry, and fluid mechanics. Dockyard dimensions. The Lothal dockyard measured 218 meters in length, 37 meters in width, and 4 meters in depth, reflecting precise calculation in proportion and capacity. Tidal regulation and water flow management. The dockyard was designed to control tidal inflow and outflow, ensuring safe docking and loading of ships. Water displacement and current calculation. The construction involved carefully calculation of buoyancy, current, velocity, and sediment control, ensuring long term functionality. Granary and trade storage. Adjacent storage facility, including a granary, indicate systematic weight standardization and trade inventory management. Standardized linear measurements. The dock and waterhouse layout follow precise geometric proportion aligning with the Harappan metrological system. Long distance trade. The dockyard facility commerce with Mesopotamia, Magan, and Dilmun, showing the Harappans' integration of mathematics in international trade logistics. So we can say the Harappans, on the basis of their different activity, showing their mathematical and calculation knowledge to the world. Here, comparative analysis with other civilization on the basis of numerical system, on the basis of urban planning, and on the basis of engineering and hydraulics. The Mesopotamian, Egyptian, and Harappan civilization each showcased unique strength in numerical system and urban planning, reflecting their cultural and environmental context. Mesopotamian utilized a base 60 number system which was especially useful in astronomy and timekeeping. Egyptian relied on cubit and fractional unit particularly for architectural and land measurement purpose. In contrast, the Harappans demonstrated early use of both binary and decimal system, indicating a high level of mathematical understanding. The Harappans, however, displayed the most advanced city planning with precisely aligned grid layouts oriented to the cardinal direction. Their mastery in water management is evident in the reservoir of Dholavira and the tidal dockyard at Lothal, showcasing engineering skills that surpassed those of Mesopotamia and Egypt. Overall, the Harappans stand out integrating mathematical precision with practical urban design, making it as one of the most technically advanced ancient cultures. This chart shows the comparative analysis of the different civilization with Harappan civilization. Feature in measurement system, Harappan civilization follow and invented decimal system and binary system. In Mesopotamia civilization, it is sexagesimal base 60 and Egyptian civilization cubit and fractions. If we see in weight system, then Harappan civilization ratio is 1 is to 2 is to 4 is to 8 is to 16 ratio, and in Mesopotamia it is just local variations showing in it, and in Egypt it is complex system like Theban, Kite and Quedet. In the category of town planning, grid based precise layout is followed by the Harappans, and irregular streets pattern is reported from the Mesopotamia civilization, and in Egyptian civilization it is showing by the aligned for pyramids. So, in conclusion, we can say the Harappans' advancement in metrology, standardized weight, and urban planning played a crucial role in shaping trade, architecture, and administration. Their mathematical precision in town layout, drainage system, and measurement unit influenced later Indian culture, leaving a lasting legacy in economic and scientific development. The continuity of their measurement system in later texts, such as the Arthashastra and in early coinage, highlights their far reaching intellectual impact. Their contributions laid the foundation for future advancement in engineering, commerce, and governance. So, on the basis of these explanations, we can say the material remains the antiquity. What we found from the different Harappan sites is just the proof for the idea that the Harappans were well known to the calculation and mathematical perspective and they well known about the different pattern of mathematics just like decimal and binary system. And if you want to learn more in this topic, then you should follow these references for your better understanding. Thank you very much for your patient listening. Namaskar.